Modern processors can execute more than 3 billion instructions per second. 3 billion. And in that flood of operations, two tiny threads of code can collide in a window so small it measures in nanoseconds, and the whole system falls apart. Not because someone wrote bad code. Because the machine itself is playing by rules most developers never see. This is the story of the invisible war happening inside your CPU, every single time you run a program with more than one thread. And by the end of this video, you'll understand not just what's happening, but why the companies building your hardware made choices that created these problems in the first place, and what programmers actually do to survive them. Let's start with something visual. Picture the Mandelbrot set. It's a beautiful, infinitely detailed fractal that lives in mathematics. To render it on screen, your computer has to calculate the behavior of millions of points in a complex plane. One point at a time, that's slow. Painfully slow. But split that work across 8 cores, and suddenly each core handles its own slice of the image. The total time drops dramatically. You go from waiting 10 seconds to waiting 1. That's the promise of parallel computing. Divide the work, conquer it faster, deliver the result. Threads are the tool that makes this possible. A thread is essentially a sequence of instructions running inside a program. One program can have many threads, all executing simultaneously, all sharing the same memory space. It sounds ideal. It is ideal until those threads need to touch the same piece of data at the same time. That's where the war begins. Here's a deceptively simple scenario. Imagine 2 threads, both trying to add 1 to a shared counter. You'd expect the counter to go up by 2. Simple math. But here's what actually happens at the hardware level. Reading the counter, incrementing it, and writing it back are not one operation. They are 3. And if thread A reads the value, then thread B reads the same value before thread A writes it back. Both threads increment from the same starting point, and only one increment actually survives. The counter goes up by 1 instead of 2. You lost data and nobody told you. This is called a race condition. The name is almost poetic. 2 threads racing to the same finish line, and the one that arrives a fraction of a second late corrupts the result. Race conditions are notoriously difficult to reproduce. They don't happen every time. They happen sometimes under specific timing conditions, which means they can hide in production code for months before a catastrophic failure exposes them. The region of code where this collision can happen has a name. Developers call it a critical section. It's the battlefield. And whoever controls access to that battlefield controls the outcome. Now, early computer scientists were smart people. They came up with elegant software solutions to this problem. One of the most famous is Peterson's algorithm, published in 1981. It uses a clever combination of flags and a turn variable to ensure that only one thread enters the critical section at a time. On paper, it's airtight. In logic, it's beautiful. On modern hardware, it falls apart completely. Here's why. Peterson's algorithm assumes that instructions execute in the exact order you write them. You set flag A, then you check flag B, then you proceed. That's the assumption, but modern CPUs don't work that way. They use a technique called out-of-order execution. The processor looks ahead at upcoming instructions, figures out which ones don't depend on each other, and runs them simultaneously, or in a different order to maximize throughput. More speed. Less waiting. The villain here isn't a person. It's optimization itself. Intel, AMD, ARM. These companies built processors that are extraordinarily fast precisely because they reorder, pipeline, and predict. Your CPU can be executing instructions from 5 different future operations while still finishing a previous one. It's impressive engineering. It's also the source of some of the most subtle and dangerous bugs in computing history. Let's make this concrete. 2 threads, one sets a value in memory. Then it sets a flag to signal that the value is ready. The second thread waits for the flag, then reads the value. The logic is sound, the sequence is deliberate. But the CPU, in its relentless pursuit of efficiency, may reorder the first thread's operations. It might set the flag before writing the value. The second thread sees the flag, charges ahead, reads garbage, and proceeds with corrupted data. No error message. No crash, just a wrong answer, delivered confidently. This is the kind of bug that makes experienced engineers lose sleep. Not because it's exotic, because it's invisible. The code looks right, the logic is right. The machine just quietly disagrees. Because software couldn't reliably solve this, hardware had to step in. The solution is called a memory barrier, sometimes called a memory fence. It's a special instruction you insert into code that tells the CPU, stop. Do not move anything past this point until everything before it is finished and visible to all cores. Think of it like a velvet rope at an exclusive event. Nothing gets through until the bouncer is satisfied that the previous work is complete. The CPU cannot reorder instructions across that line. It forces a moment of global consistency, a snapshot where everyone, every core, every cache sees the same state. Memory barriers are the hardware's acknowledgement that it created a problem and needed to provide a fix. It's almost an apology baked into silicon. But here's the uncomfortable truth. Memory barriers are expensive. They stall the pipeline. They interrupt the speculative execution that makes modern CPUs so fast. Every time you insert one, you're essentially telling the processor to stop being clever for a moment and just do what you say in order completely. That clashes with everything the hardware was designed to do. This is where the real tension lives between performance and correctness. Processor manufacturers build extraordinary machines optimized for speed. Application developers need those machines to behave predictably. Those two goals are fundamentally in conflict when you're dealing with multiple threads sharing memory. The user, the programmer writing real software, the person building the banking app or the medical record system or the navigation software, is caught in the middle. They didn't design the CPU. They didn't choose out-of-order execution. They just need their counter to increment correctly every single time. And for years, the burden fell almost entirely on them. Modern processors offered a better answer. Atomic instructions. An atomic operation is one that executes as a single, indivisible step. There is no in-between state. No window for another thread to sneak in. It either happened completely or it didn't happen at all. Two of the most important atomic instructions are test and set and compare and swap. Test and set works like this. You have a lock variable, initially 0. A thread atomically checks if it's 0 and sets it to 1 in one hardware operation. If the check succeeds, the thread owns the lock. Every other thread tries the same operation, fails the check because the value is already 1, and loops back to try again. When the owning thread finishes its critical section, it resets the lock to 0. The next thread in line succeeds, and the process continues. This is mutual exclusion. One thread inside at a time. Everyone else waits outside. Compare and swap is slightly more sophisticated. Instead of just setting a value, it checks whether the current value matches an expected value before making any change. If the values match, the update happens. If they don't, nothing changes, and the thread knows it needs to try again. This flexibility makes compare and swap the foundation of many of the most sophisticated lock-free algorithms in modern software. But here's what the hardware companies don't advertise on the box. Mutual exclusion solves the correctness problem. It does not solve the fairness problem. Imagine 3 threads all trying to acquire the same lock. Thread 1 grabs it, does its work, releases it. Before threads 2 and 3 can react, thread 1 is already back in the queue and grabs it again and again. Thread 3 might wait forever. This is called starvation, and it's a real problem in concurrent systems. A complete solution to the critical section problem has 3 requirements. Only one thread can be in the critical section at a time. That's mutual exclusion. Every thread that wants to enter must eventually get to enter. That's progress. And no thread should have to wait indefinitely. That's bounded waiting. Most naive lock implementations satisfy the first requirement. Many fail the third. The companies building these systems often optimize for average case performance, not worst case fairness. The average user never notices. The unlucky thread stuck waiting forever certainly does. Operating systems responded to all of this complexity by building abstractions. The most common is the mutex, short for mutual exclusion lock. Instead of writing test and set loops yourself, instead of manually inserting memory barriers in the right places, you call a function, acquire the lock. Do your work, release the lock. The operating system handles the rest. Underneath that clean interface, there's all of it. The atomic instructions, the memory barriers, the kernel-level scheduling, the hardware-specific behavior. The mutex is a compression of years of hard lessons into 2 function calls. It's one of the most quietly useful abstractions in all of software engineering. But abstraction has a cost. When you hand responsibility to the operating system, you trust that it made the right decisions for your use case. And sometimes it didn't. Sometimes the mutex is overkill. Sometimes it introduces latency you can't afford. Understanding what's underneath is what separates a developer who can debug a race condition from one who stares at it for a week and gives up. So what does all of this mean for you as someone who uses software built on these foundations or builds software yourself? It means that the reliability you take for granted in well-written software is not free. It's the product of deliberate, painstaking engineering decisions made at multiple levels: hardware, operating system, and application code. When that software fails, when the counter is wrong, when the data is corrupted, when the crash happens with no obvious cause, the root is often here, in the invisible collision of threads. It means that when a company ships buggy concurrent software, they may not be careless. They may be navigating genuinely hard problems with no perfect solutions, only trade-offs. That doesn't excuse shipping broken products. But it explains why these bugs are so persistent and why they require experienced engineers to find and fix them. And it means that the next time you write any code that involves shared state, the question to ask yourself is not just, does this look right? The question is, what happens when two threads hit this line at exactly the same time? Because in production, on a real multi-core machine executing 3 billion instructions per second, that moment will come. The race condition is one of computing's oldest unsolved problems. Not because we lack solutions. Because we're always chasing performance, and performance and safety are natural enemies. Every generation of hardware pushes the boundary further. Every generation of developers has to learn, sometimes painfully, where the new boundaries are. The invisible war inside your CPU never really ends. It just gets better managed, one mutex, one atomic instruction, one memory barrier at a time. If you want to understand more about how the machines you rely on actually work, subscribe to this channel. There's a level beneath the surface of every system you use, and once you see it, you can never unsee it. What other invisible systems do you want exposed? Drop your answer in the comments below. The best suggestion might be the next video.